a new study by researchers at MIT and Massachusetts General Hospital suggests the day may be approaching when advanced artificial intelligence systems could assist anesthesiologists in the operating room. In a special edition of Artificial Intelligence in Medicine, the team of neuroscientists, engineers, and physicians demonstrated a machine learning algorithm for continuously automating dosing of the anesthetic drug propofol, using an application of deep reinforcement learning in which the software's neural networks simultaneously learned how its dosing choices maintain unconsciousness and how to critique the efficacy of its own actions. The algorithm outperformed more traditional software in sophisticated physiology-based simulations of patients. It also closely matched the performance of real anesthesiologists when showing what it would do to maintain unconsciousness given recorded data from 9 real surgeries. The algorithm's advances increased the feasibility for computers to maintain patient unconsciousness with no more drug than is needed, thereby freeing up anesthesiologists for all the other responsibilities they have in the operating room, including making sure patients remain immobile, experience no pain, remain physiologically stable, and receive adequate oxygen. The research team designed a machine learning approach that would not only learn how to dose propofol to maintain patient unconsciousness, but also how to do so in a way that would optimize the amount of drug administered. They accomplished this by endowing the software with 2 related neural networks: an actor with the responsibility to decide how much drug to dose at every given moment, and a critic whose job was to help the actor behave in a manner that maximizes rewards specified by the programmer. For instance, the researchers experimented with training the algorithm using 3 different rewards: one that penalized only overdosing, one that questioned providing any dose, and one that imposed no penalties. In every case, they trained the algorithm with simulations of patients that employed advanced models of both pharmacokinetics, or how quickly propofol doses reach the relevant regions of the brain after doses are administered, and pharmacodynamics, or how the drug actually alters consciousness when it reaches its destination. Patient unconsciousness levels, meanwhile, were reflected in measure of brain waves as they can be in real operating rooms. By running hundreds of rounds of simulation with a range of values for these conditions, both the actor and the critic could learn how to perform their roles for a variety of kinds of patients. The most effective reward system turned out to be the dose penalty, one in which the critic questioned every dose the actor gave, constantly chiding the actor to keep dosing to a necessary minimum to maintain unconsciousness. Without any dosing penalty, the system sometimes dosed too much, and with only an overdose penalty, it sometimes gave too little. The dose penalty model learned more quickly and produced less error than the other value models and the traditional standard software, a proportional integral derivative PID controller. After training and testing the algorithm with simulations, the researchers put the dose penalty version to a more real-world test by feeding it patient unconsciousness data recorded from real cases in the operating room. The testing demonstrated both the strengths and the limits of the algorithm. During most tests, the algorithm's dosing choices closely matched those of the attending anesthesiologist after unconsciousness had been induced and before it was no longer necessary. The algorithm, however, adjusted dosing as frequently as every 5 seconds, while the anesthesiologist typically did so only every 20 to 30 minutes. As the test showed, the algorithm is not optimized for reducing unconsciousness in the first place, the researchers acknowledge. The software also doesn't know of its own accord when surgery is over, they add. But it is a straightforward matter for the anesthesiologist to manage that process. One of the most important challenges any AI system is likely to continue to face is whether the data it is being fed about patient unconsciousness is perfectly accurate.